In this video, we discuss the kinetics of nuclear decays. Alright, so something that is interesting about all nuclear decays is that they follow first-order kinetics. That is nice because if you know the half-life of a particular isotope, then you can actually come up with the answer to questions like, well, how much of this isotope I have left after 100 days, or 2 years, or 1,000 years. Right, so remembering here what the questions for first-order kinetics are, we remember that first-order kinetics is like this, where n is the concentration. Okay, so the concentration at any time is equal to the initial concentration that you have, and then an exponential decay that depends on the rate constant, right, and that is time. Another important thing about first-order kinetics is that the half-life does not depend on the initial concentration. And again, that is very useful. Remembering what the half-life was for a first-order process is simply equal to the natural log of 2 over k. Right, so again, it turns out that all of the nuclear decays are first-order, and every nuclear decay has a specific half-life. They can be short, or they can be very long, right? There's half-lives that go all the way from a few seconds to thousands of years. Okay? What we're going to do here is just write a nuclear decay and then ask questions that use these first-order kinetics to understand how the decay takes place. All right, the process that we're going to be interested in is the phosphorus 32. This is going to be a beta decay into sulfur 32. All right, so to complete this, we just have to remember what a beta decay is. That is the emission of an electron. And that allows us to track that our nuclear equation is correct. And there's you have 15 protons, reagents, and products, and then the mass number is 32, both in reagents and products. Right, so the half-life for this process is known. Okay, half-life is equal to 14.3 days. Right, so in about a half a month or so, if you have a sample of radioactive phosphorus 32, then that will decay to sulfur 32. About half of it will decay to sulfur 32. Okay, so then the question that we're going to be asking is, well, suppose that you use this phosphorus 32 to label some tumor. It turns out that phosphorus 32 gets incorporated into tumors because tumors are growing faster than the rest of the healthy cells, and then they need phosphorus. And if you put some phosphorus 32 around, you can see the incorporation of that phosphorus into your tumor, and you can see from the radiation emitted the dynamics and the kinetics of that tumor growth. Right. So the question is, well, suppose that we have a sample of phosphorus 32. How much of it is a sample of 1 gram? How much of it is left after 60 days? Right, so the way that you would do this is as follows. You're being asked how much phosphorus 32 is left after 60 days, and then you know your initial amount of phosphorus, which is just 1 gram. Right, so this, you can solve this simply by this, okay, n0 e to the minus kt. But the question is, well, what is the rate constant? T, you know what it is, it's 60 days, but you don't know what the rate constant is. Well, nicely enough, again, we just have to remember that the rate constant and the half-life have a very simple connection in first-order kinetics, right? So we can take this half-life equation and then just solve it for the rate constant and realize that this is equal to simply natural log of 2 over the half-life, right? So you now replace this rate constant into that expression, and you're going to get the following: natural log of 2 over the half-life times the time. Right, so let me rewrite down that equation here for the problem at hand. The mass of our phosphorus 32 left after 60 days, if we start with 1 gram of that substance, is going to be equal to the following: natural log of 2, this is going to be 14.3 days, multiplied by the time at which you're asking this question, 60 days, and that is going to give you exactly the mass of phosphorus 32 left, which is 0.055 grams. So you can see how this is a very nice and easy analysis of how quickly or how slowly nuclear reactions take place. Okay, and again, this is very useful, especially if you want to use many of these radioactive materials inside your body. You need to know how quickly those materials are going to be disappearing so that you can control radiation doses and so forth.